Hello and welcome. In this video, we're going to take a look at some applications of the derivative outside of just finding the slope of a tangent line. We can take a look at some other various different science applications or applications in economics where you'll see the derivative getting put to use. Now let's start off with one that you may already be familiar with, and that's in physics. We can take a look at many different applications in physics, but one that's probably most familiar is thinking about the position of some sort of object with respect to time. And then if we take the derivative, we're looking at the rate of change of that position with respect to time. And that's what we call velocity. So here I've got a position, s of t, measured in meters at t seconds. And it's just the function 2t cubed minus 12t squared plus 18t. And here's a graph of it off to the side. Well, there's a few things that we can do with this sort of position. If we wanted to see how position is changing, then we could take a look at velocity. And we could either measure velocity as an average or velocity as being an instantaneous rate of change, like the derivative. If we wanted to find the average velocity over an interval, that would be just like finding the slope of a secant line from 2 points on this curve. And that would be just looking at a change in position, which we call displacement in physics, over a change in time. And so we would just look at a final position at time b minus an initial position at time a divided by the difference in time. But if we wanted to find the instantaneous velocity, then at any point in time on this curve, we would be looking for the slope of a tangent line, and that's going to be the derivative. So the velocity v of t is just equal to the derivative s prime of t. And of course, being a polynomial, this is a fairly easy example. Now, if you notice on this particular curve, we have sort of two directions, a positive direction and a negative direction, where s is measured along the vertical axis upward. So as time is going on, you see from about the first 1 second here, we are traveling upwards, positive velocity, and then we are traveling downwards from 1 second to 3 seconds. And then we are traveling forward again. And that's going to give us the direction of our velocity. There are also a couple moments here where the particle seems to be just momentarily at rest. And that is where you see we have these horizontal tangent lines. And all of that is going to be shown on the graph of this velocity curve. And here you can see a drawing, a sketch of that velocity curve. Well, this is plotted in maple, so we can see exactly at those precise moments there at 1 second, 0 velocity, and 3 seconds, 0 velocity. And we can see a positive velocity, a negative velocity, and then back to a positive velocity again. Now, because the velocity is not constant, we might be interested in the rate of change of velocity, which is what we call acceleration. And we can either take a look at the average acceleration over an interval, and that is basically, again, just the slope of a secant line, but here connecting 2 points on the velocity curve. Or we could take a look at the instantaneous acceleration, which is the derivative of our velocity function. And because we're talking about the derivative of the velocity function, this is also going to be the second derivative of the position function. And if we take a look at the slopes of this velocity curve, we can see that initially velocity is decreasing, and it continues to decrease all the way down into negative velocities until eventually we reach a point where the velocity ends up as 0. And from then on, we can see that the velocity is going to be increasing towards the positive direction. And this should be reflected in the graph of our acceleration function. And here is the graph of that acceleration function. And as you can see, we have a negative acceleration, then we have a positive acceleration. We can think about this negative acceleration as being, well, we started with a positive velocity and it was decreasing. That's an acceleration in the opposite direction. This negative acceleration will take a positive velocity and slow us down to rest. And from rest, we would be accelerating into the negative velocity, and you can still see this negative acceleration. However, at 2 seconds, this acceleration is now going to be positive. And you can see that that is changing our direction. Our velocity is negative, but we start to slow down and we get to be a resting point at 3 seconds where velocity was 0. And then we end up accelerating and getting more velocity in the positive direction. So as you can see, this little change of direction here We have positive velocity but negative acceleration, which slows us down to 0 velocity, but continues to accelerate us into negative velocity until acceleration changes direction into positive, and that is going to take our velocity that's negative, bring us back to rest, and change direction so we're going to be in the positive direction. It all kind of goes hand in hand. It's important to remember that anytime velocity and acceleration have the same sign, positive or negative, then we are speeding up. And whenever we have velocity and acceleration with opposite signs, then we are slowing down. All right, well, let's take a look at a completely different example in a different science. In this example, we'll take a look at chemical reactions in chemistry. And whenever we have a reaction, we can express the reactants and products in this sort of form of showing what the reactants are and what is being produced. But we need to balance the equation. And so here you can see we've got some carbon, hydrogen, and oxygen in this reaction. And we have to make sure that both sides of the equations are balanced. And then we have these little coefficients in front to tell us how much of each reactant we need in order to perform this reaction. So let's see if we can balance this. And there we go. Now you can see that we've got 3 carbons on each side, 8 hydrogens on each side, and 10 oxygens on each side. Now, where does the calculations here turn to derivatives? Well, we may be wishing to sort of measure the rate of this reaction with respect to time. We can take a look at the concentrations here and see how quickly this reaction is taking place with respect to time. And so we could measure the concentration of reactants and products. We tend to denote those with square brackets. Right, there are 4 concentrations that we might be interested in looking at here, and they all are going to be changing with respect to time. Now the reactants here are going to be used up, so their concentrations are going to have a negative rate of change because they are decreasing. But the products on the other side here, they should have positive rates of change since they are being produced. And also you can see that we need 5 times as much oxygen as we do propane here. So its rate of reaction is going to be 5 times the speed. They're both going to be negative, but because of this sort of constant here, they are proportional, not the same. And so we can actually express some sort of equation here. The rate at which oxygen is being used up is going to be equal to 5 times the rate that propane is being used up. But we can also express these as being proportional to the rate at which carbon dioxide and water are being produced. So we actually want to maybe rearrange this equation. It's going to be a little bit more useful to write this in this form. The rate at which propane is being used up is 1/5 the rate at which oxygen is being used up in terms of concentration. Now, whereabouts can we involve the other couple products here? These are both reactants. They are going to have negative rates of change, whereas the products are going to have positive rates of change. But we can include all of this into one reaction equation. We would say that, well, these are both negatives. We'll slap negative signs on them. And they are also proportional to the rates of change of water and carbon dioxide. And using the same sort of idea here of how 5 oxygens need to be used up for every 1 propane, so the proportionality there is that the rate of change of propane is 1/5 the rate of oxygen. Then the rate of change of propane is also equal to 1/4 the rate of change of water. And of course, those are opposite signs. And it's also equal to 1/3 the rate of change of carbon dioxide. And so this quantity, all 4 of these being equal to each other, this is going to be our rate of reaction, or simply reaction rate. And just in general, whenever you have coefficients A, B, C, D in front of each of the reactants and products, you can form a very similar equation in this form, where we simply have 1 over the quantity of each molecule involved in the reaction. Now we can measure rate of reaction in concentration per time. Okay, well, let's take a look at another application in science outside of physics and chemistry, although you may see a very similar looking equation in other sciences as well. because it's not just specific to biology here. Here, if we have a basic model of an artery with some sort of blood pressure P and a length of artery L and the radius of that artery, capital R, then we can pick any point in that artery at some sort of distance, lowercase r, from the center of the artery. And we can take a look at how quickly the blood travels at that point. And this is using the law of laminar flow. Now, of course, there are many fun examples of laminar flow if you want to go on a YouTube adventure. But the law of laminar flow is here. The velocity is equal to pressure over 4 times, what is this letter, eta here? That is the viscosity, and that is multiplied by the length of the artery. And that is multiplied by the radius of the artery squared minus the distance of any point that we choose to measure the velocity squared from the center of the artery. And what we can do with this, of course, is take a look at how speed may change depending on where we put this point. So we may find that blood is not at a consistent speed everywhere in the artery. For instance, we might want to take a look at what happens closer to the center or maybe closer to the edge of the artery. What happens as lowercase r started to increase and approach capital R at the very edge of the artery? What do you think will happen to the speed of the blood in this blood flow? Well, in this case, we're not taking the derivative with respect to time. In fact, v is already measured in terms of time, but we're going to see what happens to v as we start to change the position in terms of r. So we want to find a rate of change of flow with respect to distance from the center of the artery. And this is going to be a little different. We're taking the derivative with respect to r, not t. And assuming that the pressure, viscosity, and length of the artery are unchanged, then we are simply taking the derivative of r squared minus r squared. Capital R, let's assume that the radius of this artery is fixed, and that would be a constant. Taking the derivative of r squared would just be 0, and taking the derivative of lowercase r squared, that would be what we are changing here. That would be our independent variable. We are trying to see what happens as r changes from 0 and increases towards the edge of the artery. So that would end up being a derivative of negative 2r. And then we can just simplify that slightly. And we can call this the velocity gradient. We're looking at how the velocity changes as r starts to increase. So you can see when r is a small positive number, just a little distance away from the center, then the velocity gradient is negative. And what does that mean? For a small positive r, a negative velocity gradient means that as r is slightly increasing, and we're changing from one point to a point slightly farther away, as r is increasing, we see that the velocity gradient is negative, and we see that we have a slower blood flow. So we have slow blood flow close to the wall. We have quicker blood flow towards the center. And that's how laminar flow works. Slower near the edges and faster in the center. That's all to do with the velocity gradient. And of course, there are other things that we could look at with the law of laminar flow. Rather than just the velocity gradient here, we might want to take a look at how the speed changes with respect to pressure. And we could actually have P as our variable and take the derivative with respect to P. And then at any point in time, we can see what happens to our velocity as pressure starts to build. Or we could take a look at what happens as the overall radius of the blood vessel decreases. Maybe that would be interesting to see what happens for smaller arteries at the same length, what happens to flow. All of that would just be taking the derivative of this equation, but with respect to different variables. Last but not least, we'll take a trip away from the sciences and look at another application of rates of change and the derivative in economics. In economics, we might be taking a look at something like the total cost to produce X number of units in a given month. And here's an example of a cost function. And you can see that it relies on X, but there's one term here of 5,000, and that would be what we call fixed cost. Whether we make any units or not, there are going to be some costs associated with just running this business. $40 maybe per additional unit makes some amount of sense, but we also have a couple other terms here, like a negative term, which might allow us to get a little bit of discount for making large quantities of a product and buying the materials in bulk. And some other term here that you see is also slowly contributing to additional cost for very large values of X. Well, marginal cost tells us really how much additional cost is involved with the production of one more unit. And that's not always going to be the same. Sometimes it can be a little bit cheaper just to make one more unit. And sometimes making additional units could be very costly. So for instance, what if we wanted to find the cost of the 101st item made? Well, in order to calculate that, we will take the total cost of making 101 units minus the cost of the first 100 units. And that is also going to cancel out fixed costs. We'll do that, and of course, the increase in production is only by 1 unit. 101 minus 100, well, this will give us the cost per unit. And this is going to be the cost of the 101st unit in particular. And this works out to be an increase in cost of $26.95. And we can do this over and over again. We could find the cost of the 102nd unit by looking at the total cost of producing 102 units minus the total cost of the first 101 units. But this gets to be pretty tedious if we have to do this all the time. If you notice, though, this is very similar to the average rate of change of a function. And if we were just to take that average rate of change and reduce the interval down to be as small as possible, it works out as the derivative. And that is actually a great way of bypassing this having to do all the algebra. Simply, we'll just take the derivative of the cost function and call it the marginal cost function. And this function tells us how quickly costs are increasing at any given time. What we can do is, if we've already made 100 units, we can estimate the cost of the next unit by just plugging in a production level of 100 units into the marginal cost function. And this gives us $27, which is approximately the same as calculating this additional cost manually. So in economics, we use marginal functions as a very quick way to approximate the increase for one additional unit. And we can look at marginal cost or even marginal revenue if we want to find out how much additional revenue we might get for one additional unit. So when you hear the term marginal function in economics, that typically means that we need to use the derivative to estimate the increase or decrease for one additional unit. Well, I hope that gives you at least a general sense of how derivatives are useful, not just for mathematicians, but just in general. It's definitely just, we often want to know not just about what a quantity is right now. We want to know about how that quantity is changing later, or how one quantity may affect another. Anytime you're talking about how something is being changed with respect to something, it's really just the derivative. It doesn't really matter what sort of science or economics or additional social sciences applications you're looking at. Calculus is going to be pretty useful. So even if we didn't get to dive into any of these in detail in this video, I hope this allows you to kind of go explore some opportunities of where the derivative is used outside of mathematics. Anyway, thanks for watching, and I'll see you in the next video.